field that has transformed our understanding of the universe. It encompasses theories and principles that go beyond classical physics to explain phenomena at very small, quantum, scales, extremely large scales, cosmology, and very high energies. Below is a comprehensive and detailed exploration of modern physics, including its historical development, key concepts, applications, and current challenges. 1. Historical development. Modern physics began in the early 20th century as scientists discovered phenomena that classical mechanics and thermodynamics couldn't explain. Key milestones. Blackbody radiation problem, 1890s. 1. Classical physics predicted infinite energy radiation at short wavelengths, ultraviolet catastrophe. 2. Solved by Max Planck, who proposed quantized energy levels, A equals h nu, A equals h, nu equals h nu, introducing the concept of quanta. Photoelectric effect, 1905. 1. Albert Einstein explained that light consists of discrete packets, photons, introducing wave-particle duality. 2. Led to the foundation of quantum theory. Special relativity, 1905. 1. Einstein revolutionized physics with the idea that space and time are relative and the speed of light is constant in all inertial frames. General relativity, 1915. 1. Expanded special relativity to include gravity as the curvature of space-time caused by mass and energy. Quantum mechanics, 1920s to 1930s. 1. Development of Schrödinger's wave mechanics and Heisenberg's matrix mechanics. 2. Probabilistic interpretation of quantum states. Particle physics, 1940s to 1970s. 1. Emergence of quantum field theory and the Standard Model, which describes fundamental particles and forces. Cosmology, 20th century. 1. Discovery of the expanding universe, Hubble, 1929. 2. Big Bang theory, supported by cosmic microwave background radiation. 2. Fundamental theories of modern physics. A. Quantum mechanics key principles, wave-particle duality. 1. Particles like electrons exhibit wave-like and particle-like properties, as demonstrated in the double-slit experiment. Uncertainty principle. 1. Heisenberg's principle states that the more precisely one property, e.g., position, of a particle is known, the less precisely another property, e.g., momentum, can be known. Superposition and entanglement. 1. Superposition. Particles can exist in multiple states simultaneously until observed. 2. Entanglement. Particles can be correlated such that the state of one affects the other instantly, even across vast distances. Quantum state evolution. 1. Schrödinger's equation governs the time evolution of quantum states. B. Theory of relativity. Special relativity. 1. Postulates. 1. The laws of physics are identical in all inertial frames. 2. The speed of light in vacuum is constant for all observers. 2. Consequences. Time dilation, moving clocks run slower. Length contraction, objects shorten in the direction of motion. A equals mc2, E equals mc squared, A equals mc2, mass and energy are interchangeable. General relativity. 1. Gravity is not a force but the effect of mass-energy on spacetime curvature. 2. Predicted phenomena, gravitational lensing. Black holes. Gravitational waves. See quantum field theory, QFT. 1. Combines quantum mechanics with special relativity. 2. Explains particle interactions through exchange of force-carrying particles, e.g., photons for electromagnetic force. D. Standard Model of particle physics. 1. Fundamental particles, quarks, e.g., up, down, charm. Leptons, e.g., electron, neutrino. Gauge bosons, e.g., photon, gluon. Higgs boson provides mass to particles. 2. Describes electromagnetic, weak, and strong nuclear forces but excludes gravity. 3. Applications of modern physics. A. Technology. 1. Semiconductors, bases of transistors, diodes, and integrated circuits. 2. Quantum computing, exploits superposition and entanglement for processing information. 3. Lasers, applications in medicine, communication, and industry. B. Medicine. 1. Imaging, MRI, PET scans, and X-ray technologies. 2. Radiation therapy, uses high-energy particles for cancer treatment. C. Energy. 1. Nuclear power, fission reactors and ongoing research into fusion energy. 2. Solar cells, quantum mechanics improves efficiency in photovoltaic technology. D. Astrophysics. 1. Black holes, studied using general relativity and quantum theories. 2. Cosmic microwave background, provides evidence for the Big Bang. 4. Experimental milestones. 1. Double-slit experiment, demonstrates wave-particle duality. 2. LHC, Large Hadron Collider, confirmed the Higgs boson in 2012. 3. LIGO, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves in 2015. 5. Current challenges and frontiers. A. Unification of theories. 1. Reconciling general relativity, gravity, with quantum mechanics. 2. String theory and loop quantum gravity are leading contenders. B. Dark matter and dark energy. 1. Dark matter explains galactic rotation curves. 2. Dark energy drives the accelerated expansion of the universe. C. Quantum gravity. 1. Developing a framework to describe gravity at quantum scales. D. Quantum computing. 1. Achieving fault-tolerant and scalable quantum computers. 6. Philosophical implications. Modern physics challenges traditional notions of reality, causality, and determinism. It raises questions about the nature of observation, the role of the observer, and the ultimate structure of the universe. Conclusion. Modern physics has reshaped our understanding of the universe and underpins countless technological advancements. Its ongoing exploration continues to address profound mysteries, from the smallest particles to the fabric of space-time and the vast cosmos.
Complete and exhaustive overview of entropy. Entropy is a versatile and deeply fundamental concept that spans numerous scientific, mathematical, and philosophical domains. It is often referred to as the measure of disorder, randomness, or uncertainty, and it has unique interpretations depending on the context. Below is a comprehensive breakdown of entropy, its theories, equations, applications, and philosophical interpretations. Historical development. Introduced in the context of thermodynamics by Rudolf Clausius in 1865, entropy was initially used to describe energy distribution in systems. Extended to statistical mechanics by Ludwig Boltzmann, who linked entropy to microscopic states of a system. Later, Claude Shannon redefined entropy in the context of information theory. 2. Entropy in thermodynamics. Thermodynamic entropy is central to understanding heat, energy, and work. It provides insight into the feasibility and spontaneity of processes. Key definitions. Clausius definition: S equals delta Qrev, T, where delta Qrev is the reversible heat transfer and T is the temperature. Change in entropy, delta S, delta S, delta S, delta S equals Qrev, T. The second law of thermodynamics. Isolated systems. Entropy tends to increase in an isolated system, moving it toward a state of equilibrium. Delta Universe is greater than or equal to zero. Spontaneity. A process occurs spontaneously if it leads to an increase in total entropy. Irreversible and reversible processes. In reversible processes, entropy remains constant. In irreversible processes, entropy increases. Thermodynamic applications. Efficiency of heat engines and refrigerators. Eta equals 1 minus T sealed, thought, where eta, efficiency, entropy plays a role in determining maximum efficiency, Carnot efficiency. 3. Entropy in statistical mechanics. Statistical mechanics provides a microscopic interpretation of entropy, connecting macroscopic thermodynamic quantities to the behavior of individual particles. Boltzmann entropy, S equals kBln omega S, entropy Kb, Boltzmann constant, 1.38 times 10 to the 23 J, K, omega, number of accessible microstates. Key principles. A system with more microstates, omega, has higher entropy. Entropy bridges thermodynamic properties, like pressure and temperature, with atomic or molecular behavior. Partition function. Entropy can also be calculated from the partition function, Z, in statistical mechanics, S equals kBln Z plus kBt partial differential lane Z, partial differential T. 4. Entropy in information theory. Entropy was redefined by Claude Shannon in the context of information and communication as a measure of uncertainty. Shannon entropy formula: H, X, equals minus I equals 1 NP, Xi, log BP, Xi, H, X, Shannon entropy of random variable XP, Xi, probability of outcome Xi B, base of logarithm, commonly 2 for bits, properties, maximum entropy, occurs when all outcomes are equally probable, P, Xi, equals 1, N. Additivity, for independent systems X and Y, H, X, Y, equals H, X, plus H, Y, applications, data compression, guides optimal encoding strategies. Cryptography, measures the randomness in encryption. Machine learning, entropy helps in feature selection and decision tree splitting. 5. Entropy in chemistry. Entropy is pivotal in explaining chemical reactions and equilibrium. Entropy change, delta S equals delta H, T delta H, change in enthalpy T, temperature Gibbs free energy. Entropy determines the spontaneity of reactions via Gibbs free energy. Delta G equals delta H minus T delta S. Delta G less than 0, spontaneous reaction. Delta G greater than 0, non-spontaneous reaction. Chemical examples, dissolution of salts increases entropy as ions become more dispersed. Combustion reactions involve a significant increase in entropy due to gas formation. 6. Entropy in cosmology. Entropy plays a significant role in cosmological theories and the understanding of the universe. Black hole entropy, S equals KBC3A, 4, proposed by Bekenstein and Hawking, relates entropy to the area, A, of a black hole's event horizon. Heat death of the universe predicts a state of maximum entropy where energy gradients disappear and no work can be performed. Arrow of time, the second law of thermodynamics implies that entropy increases with time, giving a directionality to time, the arrow of time. 7. Mathematical and philosophical perspectives. Mathematical properties, non-negativity, S is greater than or equal to 0. Additivity, total equals SA plus SB. Extensivity, entropy scales with the size of the system. Philosophical implications, irreversibility, entropy explains why natural processes are irreversible. Order and disorder, while commonly associated with disorder, entropy is more accurately a measure of energy and information dispersal. 8. Practical and multidisciplinary applications. Physics, analysis of engines, refrigerators, and phase transitions. Chemistry, reaction spontaneity, equilibrium studies. Information science, data encoding, encryption, and storage. Ecology, energy flow and biodiversity studies. Machine learning, feature selection, optimization techniques. Economics, models for uncertainty and resource allocation. 9. Analogies and simplifications. Entropy as disorder, often used in a qualitative sense, but not entirely accurate. Entropy as energy dispersal, describes how energy is spread across available states. Entropy as uncertainty, especially relevant in information theory. 10. Conclusion. Entropy is a universal concept that bridges macroscopic thermodynamics, microscopic statistical mechanics, and abstract information theory. It not only explains the direction of physical processes but also connects various scientific disciplines under a unified framework. Understanding entropy is crucial for grasping the underlying principles of energy, information, and the natural evolution of systems. This exhaustive note encapsulates all known theoretical and practical aspects of entropy across diverse fields of study.
What is a black hole? A black hole is a region in space where gravity is so strong that nothing, not even light, can escape it. This immense gravitational force results from a large amount of mass being compressed into a very small space. Black holes are formed through the death of massive stars, collisions, or accretion of mass over time. Key characteristics of a black hole event horizon. 1. The boundary of a black hole. 1. Anything crossing this boundary is trapped forever. 2. It's not a physical surface but a point of no return. Singularity. 1. At the center of a black hole, matter is thought to be crushed into an infinitely dense point. 2. Laws of physics as we know them cease to function here. Accretion disk. 1. A swirling disk of matter, gas, dust, and stars that orbits and spirals into the black hole. 2. The friction heats the material, causing it to emit X-rays and gamma rays. Relativistic jets. 1. High-speed jets of particles expelled along the poles of some black holes, especially supermassive ones. 2. These jets are not emitted from the black hole itself but from its surroundings. Types of black holes. Stellar black holes. 1. Formed by the collapse of massive stars. 2. Typically have a mass of 5 to 20 times that of the Sun. Supermassive black holes. 1. Found at the centers of galaxies, including our Milky Way. 2. Their masses range from millions to billions of times that of the Sun. Intermediate black holes. 1. Have masses between stellar and supermassive black holes. 2. Rare and still a subject of active research. Primordial black holes, hypothetical. 1. Believed to have formed shortly after the Big Bang. 2. Could be very small or very large, depending on conditions in the early universe. Formation of black hole. Stellar collapse. 1. When a massive star exhausts its nuclear fuel, its core collapses under gravity. 2. If the remaining mass is above a critical threshold, it forms a black hole. Mergers. 1. Black holes can merge with other black holes or stars, creating larger black holes. Accretion. 1. Black holes grow by pulling in surrounding matter or merging with other black holes. Primordial formation. 1. Early fluctuations in the density of the universe might have created black holes right after the Big Bang. Misconceptions about black holes. 1. Black holes suck everything around them. 1. Misconception. Black holes actively suck like vacuum cleaners. 2. Reality. A black hole's gravitational pull is like any other object of the same mass. 2. If the Sun were replaced by a black hole of the same mass, Earth would continue orbiting it without being sucked in. 2. Black holes are empty voids. 1. Misconception. Black holes are empty spaces. 2. Reality. Black holes are incredibly dense regions where matter has collapsed into a small volume. 3. Black holes last forever. 1. Misconception. Black holes are eternal. 2. Reality. Hawking radiation predicts that black holes slowly emit radiation and lose mass, eventually evaporating over extremely long timescales. 4. Nothing escapes a black hole. 1. Misconception. Nothing can leave a black hole. 2. Reality. While nothing can escape from within the event horizon, particles and radiation can be emitted from the surrounding accretion disk and jets. 5. Black holes are dangerous everywhere. 1. Misconception. Black holes will consume everything in the universe. 2. Reality. Black holes only affect nearby objects. 2. The universe is vast, and most regions are unaffected by black holes. Scientific observations and detection. Gravitational influence. 1. Observing the orbits of stars near black holes, such as those around Sagittarius A** in the Milky Way. X-ray emissions. 1. High-energy radiation emitted by matter in the accretion disk. Gravitational waves. 1. Ripples in space-time produced by black hole collisions. Direct imaging. 1. The Event Horizon Telescope captured the shadow of the black hole M87* in 2019. Theoretical insights. Hawking radiation. 1. Proposed by Stephen Hawking, suggesting black holes emit radiation due to quantum effects near the event horizon. Information paradox. 1. If matter falls into a black hole, does the information it contains disappear? 1. This paradox challenges current theories of quantum mechanics and general relativity. Wormholes. 1. Some theories suggest black holes could connect different regions of spacetime, creating wormholes, though this remains speculative. Evaporation and end of black holes. 1. Over immense time periods, small black holes could lose mass entirely via Hawking radiation. Role of black holes in the universe. Galactic anchors. 1. Supermassive black holes are thought to stabilize galaxies by influencing their dynamics. Star formation regulation. 1. Jets and outflows from black holes can trigger or suppress star formation. Cosmic laboratories. 1. Studying black holes helps scientists test the limits of physics, including general relativity and quantum mechanics. Black hole myths debunked. Famous black hole Sagittarius A, Milky Way center. 1. Mass, approximately 4 million solar masses. 2. Located 26,000 light-years away. M87*, Messier 87 galaxy. 1. Mass, approximately 6.5 billion solar masses. 2. First black hole image captured. Cygnus X1. 1. A stellar black hole located about 6,000 light-years away. Black holes remain among the most mysterious and fascinating phenomena in the universe, challenging our understanding of physics and pushing the boundaries of scientific discovery.